This is Lecture 2A, Introduction to Limits for Calculus 1. I'm going to include this little summary. It might help you sort of work through this introduction when you're watching it the second time. Right now it might not mean that much. The important points about limits is that limits exist and that they're easy. The actual value and the limits are two different things. So you've got the value of a function, the value of data, and the limit. Those are two different things. There's special notation for the limits, and when you use that, it really helps. Limits can occur at the edges of the domain or at the edges of your data, or they can occur at interior points. If they occur at interior points, you have to look at right and left-hand limits. And sometimes limits do not exist. They don't exist because there's jumps, because there's wild oscillations, because there's no nearby data to help you out, or because the data is there but it's all over the page. So now we're going to step through limits using data, then we're going to step through limits using functions. I want to start with an intuitive definition of a limit. I'm going to say that a limit is the endpoint of a trend, and use that to find limits on data from more or less from everyday life. You are actually very used to limits, and in fact you take them all the time. I'll give an example here of being in a lab and charging the capacitor to 10 volts. So if you're watching this capacitor charging to 10 volts and someone across the room asks you, what are you charging that capacitor to? You do not give him the values that you see on the screen. For example, you would not say, oh, 8.9 or 9.8176884. No, wait a minute. You know, it's 9.877 and that's 9.932621. You don't do that. You say you're charging it to 10 volts. You don't take it literally. You look at the trend, you see a trend, you identify it, and you identify that the endpoint is 10 volts, and you just say, I'm charging to 10 volts. Right there, you took the limit, and you used the idea. Okay, so maybe you don't charge capacitors in labs every day, but you might look at a newspaper or magazine, and you might see a graph, such as this. Here's a graph of some interest rates in 2007. Looks like for maybe weekly interest rates in 2007. And you might look at that and you might see a trend. The interest rates seem to be sort of limiting to 5.5%. Not exactly, but sort of. They're kind of oscillating about 7.5%. So you would say the limit looks like it's going towards 5.5%. That is taking a limit. You saw a trend, you identified the endpoint is the limit. Here are two more examples. If you saw a graph of the number of finches, maybe per acre, so it starts off at 1,400 and you show over the years it's just decreasing, but now it kind of looks like it's leveling off at 200. You see a downward trend and you see a leveling off. You might say the finches are tending towards 200 finches per acre. Okay. With radioactive material, we know that the limit is 0. Every time you move another time constant, these t's are the time constants, every time you move another time constant, half of the data is remaining. So you started with A0, then you got A0 over 2, A0 over 4, A0 over 8, another half of that is A0 over 16. As you go out and out in time, you will always have half of a half of a half of a half. Some people do make a big deal about it, and literally it is true. However, the trend is for the amount of material to go to 0. You take the limit and say the limit of the decay of the radioactive material is 0. So I'll give a little summary so far because these are all more or less definitions. Okay, so what we did is we looked at a graph of values. The graph showed a trend. We observed an endpoint for the trend, and that is the limit. Limits are common. They're essential to getting most jobs done. If you just proceeded literally and didn't take limits, I mean, you could talk about very big numbers and you wouldn't have any meaning to them. What limits do is they allow us to finesse a useful value or a useful answer when the literal plug and chug and brute force approaches won't give us one. Things that we ignore when taking a limit. It does not matter to us that the values or the measurements, the data, the graph, whatever, it doesn't matter that these values ever get to the limit. They may reach the limit, they may never reach the limit. We don't care. It's the endpoint of a trend. It also doesn't matter if achieving that limit is in the range of possibilities. For example, with radioactive material, it never really goes to 0, and we know that. But it only matters that the trend is heading in that direction. we have notation for limits, and it's very important that you learn it and use it, and it actually simplifies things. So first we'll start in words. In all our examples, we had two pieces to the definition of the limit. First, we had to say what the independent variable was doing. In all these cases, it was time. What was on the horizontal axis in those graphs but time? So we say, as time approaches infinity, you have to describe what the time is doing. Then you say what the dependent variable is doing. The voltage approached 10. As time approached infinity, the interest rate approached 5.5%. As time approached infinity, the number of finches approached 200, and then similarly in radioactive material, you have the same kind of statement. So the statement of limits has two parts. One has to do with what is happening on the horizontal axis. The other has to do with what the values of the graph or the y-axis are doing. We don't like to write a lot of words in math, so we use symbols. In those previous words, we used the word approached a lot. We abbreviate the word approached with the arrow. So now instead of writing out words, we just say as t approaches infinity, and you have to write the word as because that identifies which one is the independent variable. As t approaches infinity, now we can use the arrow again, v approaches 10. And similarly for all of the others. As t approaches infinity, the amount of radioactive material approaches 0. This is one way to write limits. You'll see limits written this way quite frequently. The second level of notation is a little bit different. It uses an abbreviation for the word limit, and that abbreviation is just the first three letters LIM. You still have to specify what the independent variable is doing. So as a little subscript or right beneath it, you have to say as t approaches something. So the limit as t approaches infinity of v. Now you're saying the limit is something. In math, the word is the equal sign. So you put an equal sign and you give the value of that limit. All these are the same. The limit as t approaches infinity of the interest rate is 5.5. The limit as t approaches infinity of the number of finches is 200. In all these cases, we looked at the limit as t went to infinity. There's times, though, where we might want to look at the limit at interior points. Here's an example. You can't read this very well. It was a PNG file, but it didn't, I know something's wrong with this file, but you can see the graph anyway. What this is a graph of the velocity of somebody who is skydiving, and they start at 0 because they step out of the plane right here at 0, and then as they're falling, they don't have the parachute out for the first, 40 seconds, I guess. So they're approaching a terminal velocity here of 50. So this is a limit at an interior point. They're approaching this terminal velocity at 50. After they deploy their parachute, things change and they approach a terminal velocity of 10. So taking that limit in the middle is taking the limit at an interior point. Previously we let all time always go to infinity, but it doesn't have to. There can be interior limits. Look at this expression for the terminal velocity. If you watch the lecture on exponentials, you'll recognize this as an equation of limited growth. You have a constant out in front, in this case mg over k, and in parentheses you have 1 minus a decaying exponential. There's a time constant associated with it, which is m over k, but when t is 0, the value of the exponential is 1, so you have 1 minus 1, which is why you start off at 0. Okay, that's 1 minus 1 here. Now, when t goes towards infinity, in this case it gets up there pretty fast, this decaying exponential goes to 0, and you're only left with the term out in front. The reason you have two behaviors on this is because your air resistance is different. If you're spread out like a like a flying squirrel, you have one kind of air resistance and you will be going slower. If you're all hunched up and curled up together like a bowling ball, then you'll have a different air resistance. So what happened in this case is that the parameters changed halfway through this experiment. You could have actually written this as a piecewise function with two different values of k. Okay. So that is a limit at an interior point. Once we are looking at limits at interior point, we have a new notation. For example, in this graph, I think the person had some kind of injection and they watched the buildup of substance in the blood. Okay, well, here was the buildup, and that might interest you, so you would want to know the limit here, since the data isn't exact. You sort of want to get an idea of the limit of the reaction. After this, well, the body's just eliminating the substance. So again, you have something change, and you have two different parts of your experiment. Now, if you're taking the limit at an interior point, we're going to take one at an easy interior point, one that's easy to see. Let's take it at 20. Let's say right here, well, that's kind of 20. We'll move over. You don't have a data point, and you would like to know what that is. You're kind of looking for the limit as time approaches 20. Because that's an interior point, you have to look at two limits, the limit from the left and the limit from the right. Right? The limit from the left is the one that's coming up towards it from this side, from values less than 20. And the right-hand limit is the limit you would get if you follow the curve from the right-hand side, approaching 20 from values of time greater than 20. If those two limits agree, then you can assign the value of the limit at that point. If those two limits don't agree, then there is no limit at that point. Here's the notation for right and left-hand limits. It is simply an extension of the notation for limits. We'll say that the limit, and then we have to specify what t is doing. T is approaching 20, but if we approach 20 from values less than 20, we're taking the left-hand limit, so we put that little negative sign up there. Okay, so the limit as t approaches 20 from numbers below 20 is 0.45 in this case. The right-hand limit, we write the same kind of notation, but instead of the negative sign, we put a plus, meaning that we are looking at values, starting at values greater than 20, like 30, and kind of counting down towards 20. If both of those are the same, then we can write that the limit is, in this case, 0.45. Both limits have to exist and they have to be equal. But at this point, just notice that you have this notation where you've extended the notation for a limit. Here's the limit for the notation for the limit that we had before. But if you're taking a left or right-hand limit, you have to specify whether you're starting in the left hand lower than the value you're looking for, and for the right hand greater than the value you're looking for. And that's what the negative and the positive signs mean. Sometimes limits do not exist, and there are four main reasons that limits do not exist. The first is what's called a jump discontinuity. It means you're looking at an interior point, and you can see a limit from the right, and you can see one from the left, but they don't agree because the data took a big jump. In that case, there is no limit. You might assign a value there of an average, but that is not a limit. It would be an average. Another reason a limit doesn't exist is because there is no nearby data. If you had no nearby data, you would not have a trend. For example, if you would like to know the value or the limit at t equals 100, but there are values only from 0 to 10 and 300 to 600, you have no idea what happened between 10 and 300 to give you a trend. So no nearby data means you cannot take a limit. Another reason is that there really is no limit. There is no trend. Because you have data, the data points are scattered all over, and they do not show a trend. Therefore, there's no limit. And the fourth reason is an oscillatory pattern. If the trend is that of an oscillation, of wild oscillations that never settle down, then you do have a trend, but you do not have a limit. Those are the four main reasons that limits do not exist. So here's a summary from looking at data from measurements. A limit is the endpoint of a trend exhibited by data measurements or values. Limits are common and essential to getting on with life. They can occur as t approaches infinity. They can also occur at interior points. If they occur at an interior point, there must be a right-hand limit, there must be a left-hand limit, and they must agree. At the point where you take the limit, the actual value of the data might exist. The actual value of the data might not exist. It might exist and be the same as the limit, or it might exist and be different from the limit. So the value of the data and the limit, again, are two different things. And just to summarize again, there are reasons why limits fail to exist. First is there is no trend because the data is all over the page. Second is there is a trend but it never settles down. Those would be wild oscillations. Third, there is no nearby data, so there is no trend. Or fourth, there is nearby values and they give right and left hand limits, but the right and left hand limits do not agree. Now we are pretty much going to repeat what we said for graphs, for data, and we're going to repeat that with functions. Right. So with functions, we're very used to having the value of the function. It's like having a data point. The value of the function and the value of the limit are two different things. Both are useful, but they are different aspects of the function. They could have the same value, but they don't necessarily have to have the same value. In other words, the value of the function could be the same as the limit. It could be non-existent, perhaps because you were going to divide by 0 at that point and you have to throw that out of the domain. It's not even in the domain, or for no good reason, you just don't have the value. Or the value of the function could be very different from the limit. Here's an example of a function. We're trying to take the limit at x equals 5, and for no good reason, there's no data point there. There's no value of the function there. But we can look at the left-hand limit again. So we look at the function as x approaches 5 from values less than it, 5 minus. And we work up to 5 and we find that the function is approaching 125. And we did that by looking at lots and lots of values, for example. We can find the right-hand limit by starting above 5 at 5 plus and working down towards 5 if again we find that f of x, the limit of f of x is 125, then we can say both the right-hand limit exists and the left-hand limit exists, and the two values are equal. Therefore, the limit exists at that point, and that limit is 125. This graph is the same as the previous one, only the function is defined at x equals 5, but it's defined as 200. Again, we can look at left-hand limits and get 125, look at the right-hand limit, get 125. They both exist, they agree, and therefore the limit of the function is 125. However, the value is still 200. So this just shows you a case where the limit is 125, the value is 200. And that's acceptable because the limit and the value are two different aspects of a function. Of course, there are cases where the limit and the value are the same. Here, the limit from the right as, whoa, I got left and right mixed up. Well, that's not unusual. Okay, this is the left-hand limit. Sorry. The left-hand limit as x approaches 30 from below, from negative values, values less than 30, the limit was 45. If I looked at the other one, then as x approaches 30 from values greater than 30, the limit is 45. Therefore, the limit as x approaches 30 is 45. They agree. So now we have the limit. On top of that, the value of the function at x equals 30 is 45. I put a little star there to show that. So in this case, the limit and the value are the same. When that happens, we say the function is continuous. But we have looked here with these functions at three different ideas. One, where the value of the function didn't exist, but we could still find a limit. In the second case, the value of the function existed, we found a limit, they were two different things. And here, the value of the function exists, we found the limit, and they were the same. Functions fail to have limits for the same reason that the actual data fail to have limits. First, there could be a jump in the function, a jump discontinuity. Several functions exhibit these kind of discontinuities. Two of the most famous ones are the Heaviside function and the Signum function, and they have a jump at x equals 0. There could be no nearby values. For example, the function might not be defined in the neighborhood of the point where you would like to take the limit. There could be no trend, just like there was with no data. The function could seem to be very, very scattered. One example is a function that is 1 at rational numbers and -1 at irrational numbers. It just never settles down. It doesn't really oscillate because, of course, you have more irrational numbers than you do rational numbers. Then the fourth reason is, again, wild oscillations. Some functions oscillate wildly. Sine of 1 over x, as x approaches 0, oscillates so wildly the computer can't even draw it, and in that case, as well, there is no limit. Here's the famous Heaviside function. This is Heaviside function is used frequently in electrical engineering as a switch. If t is less than 0, the Heaviside function is 0, then it jumps up to 1 when you turn the switch on at t equals 0. Of course, you can scale this and move it around, but that's basically the Heaviside function. Sometimes a different value is assigned instead of 1 at t equals 0, but this is pretty standard. Okay, if I look for the left-hand limit as x approaches 0 from the negative values, the Heaviside function is approaching 0. If I look at the right-hand limit as x approaches 0, the Heaviside function is approaching 1. So there is a right-hand limit, there is a left-hand limit. They do not agree. Therefore, the limit does not exist. This is an example of a jump discontinuity. Another function that exhibits a jump discontinuity is a signum or sine function. The sine function just takes the value just gets the sign of the argument. If it's positive, it assigns at 1. If it's negative, it's minus 1. At 0, there really is no sign, so it has a value 0. The left-hand limit, as x approaches 0 from negative values, is minus 1. The right-hand limit, as x approaches 0 from positive values, is plus 1. The right-hand limits agree. They don't agree. They exist. They don't agree. Therefore, there is no limit. In this case, the value of the function is 0. Two different things, limit and value. Here's the other reason why functions fail to have a limit, and that is wild oscillations. This function is a sine of 1 over x. If we let x go to 0, these oscillations get wilder and wilder. It is always oscillating between plus or minus 1. It never converges on any particular value. Therefore, there is no limit. There's no right-hand, left-hand limit or anything. There just isn't a limit. That's due to wild oscillations. When we talked about the actual data from an experiment, we said that perhaps you would have no nearby data points in order to take a limit. We have to address that with functions as well. We do that by saying that for the limit to exist at some point, the function must be defined in a neighborhood about that point, and I'm calling it t0. It does not have to be defined at t0 because we're looking for a limit, not a value, but it has to exist in the neighborhood. The neighborhood is an open interval about t0. And that will give you all the data, like the nearby points that you need to establish what the limit is if it does exist. If you're looking for the limit at the edge of a domain, you relax this condition and say you only need the function to be defined on an interval on the interior of that point, interior of the domain as it reaches that limit, as it reaches the edge of the domain. And again, for interior points, the right and left-hand limits must exist and must have the same value. Everything was pretty similar between functions and the measurements up to this point, but with functions we have to address 3 issues. One is the idea of infinite limits. Let me get the marker here. We have to infinite limits. Well, okay. The other is the limit at infinity, and the other are asymptotes. These 3 are actually 3 separate problems, but they occur together so frequently that they end up, you kind of have to consider them sort of all at once. The first thing we'll look at is limits at infinity. If the function approaches a finite value as x or t approach infinity, that value is called the horizontal asymptote. Okay. So now we have a limit at infinity and horizontal asymptote both combined. So what we're looking at is the behavior of the function as x or t approach plus or minus infinity. When we can establish that, we call that the horizontal asymptote. Sometimes, as x or t approaches infinity, the function just increases without bounds. Then the limit is infinite. So we move to 2, infinite limits. If a function increases or decreases without bound, as the independent variable approaches a value, we agree to say that the limit is infinite, and I'll demonstrate that later. That's kind of an abusive terminology here because nothing can equal infinity. But with limits, we do accept that. We really just mean that the function is increasing or decreasing, but I think basically we don't want to write all that out, so we just say the limit equals infinity. And for infinite limits, if you approach an infinite limit at an interior point, okay, that point is called a vertical asymptote. Of course, it can approach an infinite limit as x or t approaches infinity, but in that case it doesn't have a name. So you see these three concepts, infinite limit, limits at infinity, and asymptotes, are all sort of overlapping. Here's some examples. This is an example of a horizontal asymptote. In this case, we're looking at the function we looked at before, the one that had wild oscillations as x approached 0. But as x gets bigger and bigger, this function approaches the line y equals 0. So its limit as x approaches infinity is f of x is approaching 0. The limit is 0. This is its horizontal asymptote. So the horizontal asymptote is the line y equals 0 because the function approaches it as x approaches infinity. I've just written on this slide what I said earlier. If a function increases or decreases without bound as x approaches, we'll say x naught, then the question is, does the function really have a limit? I'm not going to say yes or no. I'm going to say the answer is handled in the following way. If we observe this situation, then we agree to say that the limit equals infinity. For the exponential, for example, does e to the x have a limit as x approaches infinity? We observe this and we write that e to the x blows up. We agree to say that the limit of e to the x as x goes to infinity is infinity. What we really mean is that x increases without bound. If we look at the log function, we ask, does it have a limit as x approaches 0? Well, we observe, and of course we can write with no problem, that as x approaches 0, the log of x approaches negative infinity. Then we agree to say that as x approaches 0, the limit of the log of x is or equals negative infinity. What we really mean is that the log of x decreases without bound as x approaches 0. In this case, x equals 0 is a vertical asymptote of the log function. So here's a summary of this introduction. A limit is the endpoint of a trend exhibited by data, measurements, values, a function, a graph. Limits are common and essential to getting on with life, especially getting on with calculus. For a limit to exist at a point, I lost my marker, sorry. For a limit to exist at some point x0, the function, or measurements, must be defined in an open interval about x0. You must have nearby data. The function does not have to be defined at x0 because the value of the function and the limit are two different things. If x0 is at the edge of the domain, the function data must be defined on an interval only on the interior side. There's like 3 pages to the summary. Okay, limits can occur as x approaches infinity or as x approaches the edge of the domain of a function. They can also occur at interior points. If they do occur at interior points, there must be a right-hand limit and a left-hand limit. Both must exist and both must have the same value. Here's how we write limits. Either, both are acceptable notation, and by convention, we accept plus or minus infinity as a value for L. Really meaning that the function increases or decreases without bound. We don't mean that there is a number at infinity and L is equal to it. Now at the point where you take the limit, the actual value might not exist. The value might exist and be the same as the limit. The value might exist and be different from the limit. All three are acceptable because limits and values are two different things. A limit fails to exist because there is no trend. The data or the function values are all over the page. Or for the second reason, there is a trend but it never settles down. That's wild oscillations. Or there is no nearby data and so you cannot pick out any trend. And the fourth reason is that the right and left-hand limits either don't exist or if they exist, they don't agree. Surely you're not going to learn limits from just watching this very brief introduction. You can watch this again. You can also go back to the book, read the chapter in the book. You'll notice in chapter 2, from what I'm calling chapter 2, is only limits. The homework problems are only have to do with limits. All the ones that have to do with derivatives and the application of limits, I've put with chapter 3. So all you have to do in what's called chapter 2 for this class is concentrate on limits. The written summary is a little more detailed than what I've given here with the audio. Again, look at the book, whatever book you're looking at, Thomas, Stewart, whatever you're looking at, read it again, and then start trying to do the homework and see how it goes.